Good day to our lecturer, T.S. Dr. Hamali, and my fellow colleague. Today, my team and I are incredibly proud to present our project under Tinta Overheat Technologies, or simply TTO Tech. Our guiding core principles are simple: stabilize, support, and perform. Guided by this philosophy, we identify a universal daily pain point for drivers and commuters alike: liquid spill and vehicle console messes caused by static, outdated cup holder design. To solve this, we engineered a dynamic solution. Today, we are excited to introduce our innovation, the TTO Tech Gyro Cup Holder. Before we dive into how the product works, let me introduce the team behind the engineering. Every innovative product requires a cross-functional team to take it from a concept to a functional reality. Leading the project management is myself, Faris Shaban, managing our data collection, customer needs analysis, and documentation is Afrina Amani Huda. On the technical front, Hafiz drives our CAD engineering and technical development, while Noah Atika spearheads our presentation design and drafting. To ensure the product functions flawless, Rushton oversees our rigorous testing and quality control protocols. Finally, managing our manufacturing budget and cost optimization is our finance and procurement officer, Natasha. Together as a unified team, we handle everything from initial market research to the final fabrication log. Now, let's look at the core features that set our product apart from standard market alternatives. Our gyro cup holder tackles the issue of vehicle motion through three main pillars. First, it features a dynamic self-leveling mechanism. By employing a multi-axis gyroscopic gimbal architecture, the inner basket reacts instantly to vehicular tilts, sudden turns, and bumps. This gravitational response ensures that your beverage container stays perfectly upright regardless of the terrain. Second, stabilization is nothing without control. We integrated smooth motion dampening using low friction pivots and counterweights. This key engineering detail eliminates aggressive shaking and harmonic oscillations, effectively neutralizing the momentum that causes liquids to slosh over the cup stream. Third, we focus heavily on physical compatibility and market integration, which we have noted here alongside our cash flow goals. The assembly is engineered with a highly compact footprint designed specifically to retrofit seamlessly into existing vehicle mounts, marine console, or workspace desks, while adaptively securing a wide variety of cup sizes. Next, my team member will walk you through our target market and how we benchmark this design against existing market competitors like the Proton Saga built-in holders and RAM mounts. I will pass the floor over.
Hello, my name is Afrina Amanihuda binti Zulkarnain and I'm responsible for the research and documentation engineer. So for our market research, our objective is mainly about identifying customer need and market opportunities for our product, analyzing existing product in the market to compare the pros and cons for between our product and existing product. Next is defining a product specification and selecting the best concept for development. And lastly, prepare a project documentation. So our target market is car owners and e-hailing driver, for example, Grab and Maxim. The reason for our product is because when there is frequent use of drink while driving, it also increases the chance of spilling drinks. So our main target for our product is to reducing drink spills in vehicles. Next, I will explain about our benchmark. This benchmark is showing the difference between Saga cup holder designed for the car itself, a RAM mount level cup, and our own 3D printed gyro cup holder. So the criteria included the spill protection, space efficiency, ease of installation, adaptability to road condition, aesthetic customization, the price, the portability, and the ease of manufacturing. So as we can see, our 3D printed Garuka holder balance between functionality, cost, portability, and user convenience, making it the most best design between standard cardholder, which has a lower benchmark from our own product, and a more level cup that has a higher benchmark than our product. So this is our product specification. As you can see, the outer ring diameter is 158 millimeter. The inner ring diameter is 137 millimeter. And the total assembly height is 228 millimeter. And the net weight for the product is 136 gram. And the whole size compatibility with the holder in car is 35 to 54 millimeter. And the material used is ABS. So this is our Gantt chart. So we start our project by 13 May, and during week 1, we focus only doing the project initiation and planning that include the problem identification and market research, a product selection and organization chart, and a baseline Gantt chart preparation. So by week 2, we already done the design requirement and space that included the mission statement development, data collection and customer analysis, and also a product design specification drafting. So by week 3, we do the concept generation and selection, which is focusing on a material sourcing research and budgeting, and also each member individual idea sketching and brainstorming. And then next, by the sketching and brainstorming, we move to the concept screening and scoring metric education to conclude the best design that complete all the customer need. So next, as you can see, for the detailed design and technical validation, for the 3D CAD design and technical drawing, we actually done it exactly by the planning time, which is in week 5. And for the prototype printing, prototype assembly planning, and the testing protocol, the actual time is does not align with the planning time, as we actually has print the 3D printing exactly as the planning time. But we encounter a problem, which is the printing size is not the same as the drawing. So as the drawing size. So we have to reprint it all again. So the finalization and handover. So all of the final design freeze and visual drawing, report writing and synthesis, and the final review and the project submission does align with the planned time.
Good morning, everyone. My name is Nur Aina, and I am the Finance and Procurement Officer for this project. I will explain our cost analysis. First is the machine cost. The estimated cost was Rm 6.30 based on a printing time of 9 hours. However, the actual printing time was 11 hours. So the machine's cost increased to Rm 7.70. Next is the labor cost. The estimated cost was Rm 3.50, while the actual cost was Rm 4. This includes designing the product, setting up and the printer, monitoring the printing process, and finishing the product. For the material cost, the estimated cost was Rm 6.84, but the actual cost increased to Rm 15.68. This is because the final product used 250 grams of ABS filaments, which cost Rm 56 per kilogram. There was no standard part cost because all parts were 3D printed. The consumable cost increased slightly from Rm 1.02 to Rm 1.50. This includes sandpaper and cleaning material used during finishing. The packaging cost increased to Rm 2 to Rm 2.50. This includes the box, label sticker, and protective wrapping. After adding all the costs, the estimated subtotal was Rm 19.84. while the actual subtotal was Rm 31 ringgit and 38 cents. Then we added a 50% markups to determine the selling price. The estimated selling price was Rm 29 ringgit and 76 cents, and the actual selling price was Rm 47 ringgit 7 cents. In conclusion, the actual cost was higher than the estimated cost because the product used more material and took longer to print. Even so, the final selling price is reasonable for the durable and customized 3D printed product. Thank you.
My name is Nur Atika, and as the Design Presentation Engineer, I will be presenting our product design and technical engineer specification. On the left side, we display our primary 3D CAD prototype. This model features the compact gyroscopic ring design with self-adjusting dynamic ring that secretly hold different type of things. We designed it with a compact size so that it fit easily into standard vehicle cup holder without affecting the driver or comfort or movement. On the right side, we present a realistic digital rendering of the prototype in real-world environment. This image highlights the product's clean, modern, and premium appearance. Instead of creating a bulky accessory, our goal was to develop design that blend naturally with modern vehicle interior while providing reliable container stability. This makes the product suitable for everyday driver as well as hailing driver who value both functionality and style. This is our final assembly engineering drawing. To provide absolute precision for future physical prototyping and mass manufacturing, we have provided 3 standard orthographic projections: the top view, front view, and side view, complemented by the 3D isometric view on the right. Our Gyro card holder is constructed using 10 distinct modular components. At the core of the dynamic structure are the inner ring and the outer ring, which form for our leveling gimbal. To secure beverage tin of various sizes, we developed an adjusting clamping mechanism consisting of the center cup holder, 6 T-slot, 6 internal grippers. This provides a snug rattle-free grip around the cans during rough transit.
As you can see from our setup matrix, we configured our printer with a nozzle temperature of 250 degrees Celsius and a build plate temperature of 105 degrees Celsius. These thermal profiles indicates that we are printing a high temperature engineering filament. We maintain a steady print speed of 50 mm per second with a standard layer height of 0.2 mm to strike a balance between precision and production efficiency. The infill density was set quite high at 40% to guarantee a strong mechanical properties, and we activate a stopper structures to manage any complex geometries or overhang safely. To dive a bit deeper into what happened on the 21st of June, this table outlines our specific post-processing steps for each component. For both the T-slot and the gripper, our main quality control issue was the surface weren't entirely smooth. We addressed this by meticulously rubbing the surface down using high-grade 1000 CW sandpaper. For the cup holder, our primary post-processing operation was support removal, which was executed with no issues right after the print finish. Lastly, after all individual components were prepared, we noticed that the final curing phase left the surface finish looking slightly dull instead of shiny. We gave the assembly a premium look by applying a final touch-up with dedicated shining spray. Moving on to our actual timeline, let's take a look at the fabrication log. The entire process spanned across 4 days, from the initial digital preparation to the final assembly. On June 18th, we kicked off with a 3D print slicing and preparation, encountering absolutely zero issues during the digital setup. This was followed immediately by the active 3D print process, which ran from June 18th to June 19th smoothly. On June 20th, we entered the post-processing and sanding phase. Here, we noted a slight challenge. The components came off the bed with a rough surface texture. To resolve this, we manually sanded the component surface using sandpaper. Finally, on June 21st, we successfully wrapped up the project with a component assembly, noting no remaining issues. Our last slide for fabrication covers engineering change order number 1, which highlights how we handle an unexpected geometric deviation during production. As shown in the caliper measurement, our initial prints suffered from an error where the scale unexpectedly decreased or shrunk. To ensure the product satisfied customer expectation and stayed universally compatible, we implemented a design scale adjustment and reprint the parts. Looking for the overall effects of the engineering change, functionally, it drastically improved compatibility by bringing the parts back up to the required scale. Second, safety-wise, it had no negative effects and actually enhanced user control over the final mechanism. Third, from a financial standpoint, it did result in an increase in our production costs due to the material and time used for the reprint, but it ultimately ensured we delivered a high-quality, fully compatible product.
Assalamualaikum and good day everyone. My name is Rajdan and I am the Quality and Testing Control Engineer for the Gyro cup holder project. So for quality assurance, we develop a standard operating procedures that guides all inspection activities throughout the production process. The inspection process is divided into 3 stages. First is incoming inspection, where all the raw materials and components are checked upon arrival. We verify the material type, specification, dimension, and inspect for any visible defect. Second is in-process inspection, where we monitor the manufacturing process. During this stage, we ensure machine parameters are correctly set, dimensions remain accurate, and sufficient material are available for production. Finally, final inspection is conducted after the product is complete. We check overall dimension and tolerance, perform functional testing, and evaluate the critical to quality characteristics to ensure the product meets customer requirements. This SOP helps maintain consistent product quality and minimize manufacturing defects. This fishbone diagram was developed to identify potential causes that may affect product quality. The causes are categorized into 6 main factors, which is method, material, machine, manpower, measurement, environment. So as you can see, like method, we have an unclear SOP, outdated work instruction, and so on. For material, we have incorrect material selection and material shortage. For machine, we have equipment misalignment, calibration issues, machine breakdown. For the manpower, we have lack of skill, insufficient training. For measurement, we have uncalibrated measuring tools, inaccurate inspection equipment, and lastly, for environment, we have dust contamination and suitable temperature. So by identifying these root causes, we can take preventive action and improve the overall quality of the Gyro cup holder. For this slide, present the test plan developed to verify the performance and quality of our product. Several tests were conducted, including assembly verification tests, functional performance tests, safety inspection tests, and mechanisms tests. So the purpose of this test is to ensure the Gyro cup holder performs reliable under normal operating condition and meets customer expectation. All testing procedures were documented and evaluated according to predefined acceptance criteria. After completing the testing activities, the results showed that the Gyro cup holder successfully met the required performance objective. So the product that demonstrated good stability during movement, maintained the cup position effectively, and showed satisfactory structural strength. No critical defects were observed during testing, and all major functional requirements were achieved. This result indicate that the design is suitable for its intended application and ready for the further development and improvement. We are reviewing the critical to quality or CTQ characteristic of our product. This ensures that our manufacturing meets the highest standard of safety and performance. So looking at the CTQ characteristic chart, we evaluate 6 key areas as smoothness, fastener tightness, material integrity, user safety compliance, surface finish quality, and safety level visibility. So most categories are showing 0 defects, meaning they are compliant and within specification. However, we have identified 2 areas requiring attention. Fastener tightness, we recorded 1 defect because the gripper cover and gripper cannot be fully twisted. Surface finish quality, we also recorded 1 defect due to minor cosmetic issue despite a uniform finish being achieved. So while the majority of our checkpoints such as edge smoothness and safety level visibility are pressing, this identified defect will be addressed immediately to ensure full quality compliance. Thank you for your commitment to our quality control standard. Moving on to our quality and safety assessment, we have carefully analyzed potential risks in our 3D printing process and product performance. As shown in diagram, we identified several key issues ranging from dimensional inaccuracies and warping to structural concerns like layer delamination and assembly misalignment. For each of these, we have defined a clear mitigation strategy. For instance, to combat dimensional errors, we are implementing strict calibration procedure using caliper. To address structural integrity, we are optimizing bed temperatures and fine-tuning our layer setting. We are also proactively managing user safety by addressing potential surface defect and sharp edges that could arise during the manufacturing process. Ultimately, this control ensures that the final product is not only accurate but also safe and durable under load. That concludes our overview of the quality control measures we've put in place. Thank you for your time and attention. We are now happy to perform you this product.